I invite Professor E S Raghavan, a very distinguished analyst, to give his talk.
It is with great pleasure that I am able to be part of this superb conference in honor of Professor CR Rao, my thesis advisor. I'm deeply touched by the efforts which have been put in by Manipal University, headed under the direction of Professor Manjunath Prasad and his team of excellent students. CR Rao, when I joined in 1962 at the Indian Statistical Institute, CR Rao was so compassionate to me, and he allowed me to have my own freedom to continue with whatever area I wanted to do research in. And I chose to work in statistical decision theory and change it from there to game theory. And he said, you continue on. And I was also interested in matrix theory at that time. He said, why don't you do lectures on matrices and even write a note? That's how I came to appreciate his the way he treated graduate students with freedom and compassion. When I finished my PhD, the day I submitted my thesis, there was a call from England from George Barnard, the famous statistician, who wanted somebody to join him in the department, the new department of the University of Essex. CR Rao suggested immediately my name, and that's how he changed my whole life. So all I can say is, Guru Brahma, Guru Vishnu, Guru Devo, Maheshwaraha, Guru Sakshat Parabrahma, Tasmai Sri Gurave Namaha. My respects to this great statistician, a mentor, and everything. With this, I would like to start my lecture. I am presenting my talk for the first time on a connection between matrix games and linear complementarity. This is a joint work with Deepti Dubey of Shivanada University, Professor S.K. Niyogi of the Indian Statistical Institute, and myself. It has two parts. The first part is linear complementarity problem, and the second part, it has to do with zero-sum 2% matrix games, which shows the connection. What is linear complementarity problem? Suppose you are given an n by n real matrix M, and you are also given an arbitrary real column n vector Q. When these two are given, for every arbitrary Q, can we find a solution to the system of equations W equals mz plus Q as equation 1. W and Z are vectors non-negative, all coordinates are non-negative, and W and Z are orthogonal, namely each coordinate wise Wi, Zi is 0 for each I. Any solution to 1 and 2, namely W equals mz plus Q and W non-negative, Z non-negative, is called a feasible solution. And any solution to 1, 2, and 3 is called a linear complementary solution. Namely, you should satisfy 1, 2, and also W and Z orthogonal. Now, before trying to do this one, when we look at this system of equations and inequalities, if you consider only 1 and 2, the set of solutions W and Z, if it is non-empty, is a convex set. So we are not searching for any arbitrary point of the convex set, and it is a polyhedral convex set. So we are concentrating mainly on looking for extreme points of that set, and among them looking for those which will satisfy also condition 3. Now, instead of searching for that one straight away, Lemke came with the following idea. Consider an auxiliary system where W equals mz plus q and plus a scalar z0 times the vector with all coordinates 1, which is the vector E. And again wz, z0 non-negative, and w and z are orthogonal. No matter what m is, what q is, you can always find a z0 sufficiently large that will solve 4, 5, and 6 with no sweat. Incidentally, any solution to 1, 2, and 3, namely any solution which satisfies 1, 2, and 3 will automatically satisfy 4, 5, and 6, provided you put z0 as 0. Unfortunately, on the other hand, any solution to 4, 5, and 6, until and unless z0 is 0, may not satisfy even 1 and 2. That means it may not even be, the original problem may not even be feasible, and yet you may find a solution which with positive z0. So we first impose what is called a non-degeneracy assumption, which is the usual assumption in all areas like linear programming, simplex method, etc. Under the non-degeneracy, a pair of coordinates wi and zi as mate variables for each I. Any basic feasible solution to 1, 2, and 3, 1, 2 will satisfy 3 if and only if exactly one of the mate variables is basic. That means either wi is 0 or zi is 0, but not both. So in all honesty, our problem under non-degeneracy is searching for such a solution. We will motivate what we have in mind with a simple example. Consider the matrix M, 2 by 2 matrix, 5, minus 4, minus 3, 6, and Q as 1, minus 3. Suppose Q is positive, we have no sweat. Our original problem can be very easily solved. Simply, let me indicate again. The original problem can be solved if Q is positive or non-negative. All you need is put Z equals 0 and W becomes Q, and you have everything satisfied. So the real difficulty is only when Q has some negative coordinates. So we start with such an example. Now we need to develop first a feasible solution that satisfies 4, 5, and 6 for a suitably large Z0. Now the moment you increase Z0, all of them will be satisfying those 1, 2, 3 conditions. And so that means these solutions form an edge of unbounded length. Now this unbounded ray will have one end at an extreme basic feasible point, and like we use the simplex tableau method to first locate such a point, satisfying 4 and 6. So what we do is you make W1 and W2 as basic variables, and what we see is we have two equations. So W1 minus 5Z1 plus 4Z2 minus Z0 equals 1. W2 plus 3Z1 minus 6Z2 minus Z0 equals minus 3. This is your initial table, but unfortunately W2 is minus 3. So we need a feasible solution. So the first thing which we do is to get rid of W2 and replace it by the auxiliary variable Z0. This is the first starting point. So initially we bring Z0 into the basis. The standard technique of row operations will help us to make Z0 as the unit vector, and its number one appears at the cutting of W2 row and Z0 column. So we get the next table. So W1 and Z0 are now the basic variables, and the current solution is W1 is 4 because the solution is identified with the last column Q. W1 is 4, Z0 is 3, all the other variables are 0. Now we notice the only positive variables are in the basic variable column. This is clearly a solution to 4, 5, and 6. We reached this table first time by making W2 non-basic. Now what we notice is not only W2 is non-basic, its mate Z2 is also non-basic. Unlike W1, which is basic, its mate is non-basic. W2 is non-basic. Z2 is also non-basic. Only recently we made W2 non-basic, from basic to non-basic, or non-zero to thing. Now we bring the mate of W2 into the system. That means the column corresponding to Z2 enters the basis as in the simplex method, and we use the usual ratio test to determine who leaves. Should W1 leave or Z0 leave? If Z0 leaves, we'll be back in W2. So it's actually, it is only W1 which will leave. And that is determined by the star entry which we notice in this table. Now, Z2, in the next step, because we have brought in Z2, so that's the table which we get. So the column corresponding to Z2 will be 1, 0, and the solution is Z2 is 4/10, Z0 is 6/10. But we are still not able to eliminate Z0 from the system. What we now try to do is, we look at the solution. Now Z2 is positive, W2 is 0. Z1 is 0, W1 is also 0. Just previously we had W1 into the system, which we dropped out. So now we made from basic to non-basic. So we try its mate to become basic. Its mate Z1 has to become basic, which means the column corresponding to Z1 enters the basis. By the ratio test, the only allowable condition is, because if you look at the Z1 column, the first entry is negative, the second entry is starred entry is positive. So we can take the ratio only on the Q column with the Z1 column, the ratio corresponding to positive entries, and that makes it necessarily that Z0 must leave and Z1 must enter. And that's what happens now. We find the only one to vacate is Z0 by the ratio test. Now we have come to the solution. Basically, Z1 and Z2 are positive, W1 and W2 are 0. They are complementary, and then they satisfy all the conditions. Z2 is 12/18, which is 2/3. Z1 is 1/3. W1 is 0. W2 is 0, and we have arrived at a solution. We were simply lucky. I knew that for this class of matrices, Lemke's algorithm will work. For example, our procedure has to fail when M is this matrix with all entries negative and Q also negative. What will happen is we may be able to find a positive Z0 such that Z equals 0 will satisfy the conditions. But unfortunately, by this pivoting method, you will never let Z0 leave the basis. That is you can try it with a simple example, or the same example. Now we would like to show that we can give a class of matrices with certain conditions guaranteeing the termination when they admit a feasible solution. This is what we want to study via zero-sum two-person matrix games. Now, you look at this polyhedral set. The idea is that we start from an unbounded ray to one extreme point, and we travel only along this edge, where all these edge points satisfy the complementary slackness condition. So it is some kind of an one-dimensional lines which are going, and the real thing is, if you see a thicker line now, the thicker line says that is how the path is now moving. The path movement is equivalent to saying from one tableau you move to another tableau by adjacent extreme points. But then it might, the moment it stops, it won't move once Z0 becomes non-basic. But we are not sure whether the path will go that way, or it could also go the following way. You can see the new path. It will terminate provided Z0 is still non-basic. But if Z0 is basic, it may go and then reach another extreme point. I can call that extreme point, 1 minute. Other extreme point which I have noted. From there, it may go to another unbounded ray, which means we have lost our effort to solve the problem. So this is what is called, the first one is called the primary ray. The second one is called the secondary ray. If the matrix is not in the right structure, what could happen is we may end up with a secondary ray, in which case the problem is not solved. It doesn't mean that the problem has no solution. It means that my algorithm is not able to solve the problem. So we have only one algorithm right now. There is no other algorithm. That is the algorithm of Lemke, which lets you move from table to table only because the complementary path travels in such a way that you enter through a corner and you exit through its made corner. So the made is made positive and one of them is made zero, like that. So that's all we are doing now. But when are we sure that it will terminate at a solution? That's the final question. And to understand that question, initially many attempts have been made by Eves, by Garcia, and quite a few people, including Lemke. But what I realized is it is closely connected to a game theoretic problem, and that's what I now want to talk about. So we would like to show that we can give a class of matrices with certain conditions, guaranteeing the termination when they admit a feasible solution. We want to study through game theory. What is that? So I give a small basic baby introduction. What is a matrix game? We consider our own matrix M as the matrix which two players play. Player 1 is the column player whose interest is to get the maximum amount from player 2, the row player. So he chooses secretly a column, and player 2 chooses secretly a row. But they may not necessarily choose them with exact probabilities, or with exactly one of them. They may also perform a chance experiment by which they may select a row or a column. So the chance experiment is with probabilities P1, Pn, the column player chooses the columns, and the row player chooses with probabilities Q1, Q2, Qn. And if the jth column ith row is reached with probability Pj, Qi, then the income to player 1, namely the column player, is Mij, and he receives this income with probability Pj. So his expected income is at least Vm for a suitable P, where Vm is a unique number which has the following property. While player 1 column player can hope to get on the average Vm independent of what player 2 does, same way player 2 can also select his rows with probabilities Qi, guaranteeing that his loss is no more than Vm, and that Vm is called the value of the game, and von Neumann proved there exists such a Vm. And these P and Q are called good strategies for the two players. They are called optimal for 1 and optimal for 2. Now let me put the condition which I want to impose on this matrix. Condition 1, that the matrix game M has value 0. 2, if I take the transpose matrix and consider every one of its principal submatrices, they all have value non-negative, where column player is the maximizer as usual. So now we are ready to state the main theorem. The following is the main theorem which connects linear complementarity with game theory. Let Vm be 0 and Vm transpose Kk be non-negative for all principal submatrices. What do you mean by principal submatrix? You choose if you choose the 4th, 9th, 15th row, similarly you choose the 4th, 19th, 15th column, that such submatrix is the MKK, where K is 4th, 9th, and 15th. So like that, every one of those submatrices, if you calculate their transpose matrix value, it must be non-negative. That's not the only condition. Now the second condition is, for any optimal U mixed strategy for the column player, there should be an optimal X for the row player, such that U and X share the same positive coordinates. That is, if Ui is positive, Xi must be positive. If Ui is 0, Xi is 0, and conversely. Further, we need one way condition. M of Ui, which is the expected income to the maximizer, when player 2 chooses ith row is 0, the same way in M transpose X, I must also be equal to 0. Once this is given, the theorem says the linear complementarity problem can be processed by Lemke's algorithm with a solution to 1, 2, and 3, provided 1 and 2 have a feasible solution. We can always check for feasible solutions by simple linear programming. So this way we know that when this condition is satisfied, the theorem guarantees that if you start with a feasible solution, there is no way that if you start from the primary unbounded ray, you will not hit another secondary unbounded ray. You have to stop at an extreme point or a basic feasible solution, which is complementary. The key conditions, because I'm not giving the proof is long and quite a little bit involved. With the limited time, I cannot do that. All I can give you is the feeling of it. The conditions of the above theorem guarantees the existence of two diagonal matrices, lambda, capital lambda non-negative, capital omega non-negative. Omega can also be assumed as non-negative as well as positive, such that lambda m plus m transpose omega u is 0, where u is optimal for 1 and x is optimal for 2. So the Lemke's algorithm applied to the auxiliary problem hits another unbounded ray different from the primary ray if and only if the system 1, 2 is infeasible. So that is these are the two key ideas of the proof. They are a little bit long and you need to manipulate to get them. If people are interested, I can send later the paper. This is the picture which we took. In fact, Teja, CR Rao's daughter, she took when we went to visit them 3-4 years back. And Mrs. Rao was so happy. We took some mangoes and she was like a child. She was saying, I want mangoes. I want mangoes. What the ma, she was telling. No, she said, I want mangoes. And then we stood there and I prostrated 4 times before this, my great teacher, and got his blessings. And this is one of my most memorable pictures. And another one, which I also want to show, is the following. So this is a few years back, quite a few years back, when Professor Rao was honored by the University of Wisconsin-Madison, and I went all the way to Madison to see him, and we were in some GM Naidu's house. That's where we sat, and then this is a picture when I was probably much younger. These are the 2 pictures which I have of Professor Rao, and I cherish them like anything. Guru Brahma, Guru Vishnu, Guru Devo Maheshwaraha, Guru Sakshat Parabrahma, Tasmai Shri Gurave Namaha. Thank you.
Thank you, Professor Raghavan, for the lovely talk and sharing your memories. Wonderful. I think we have time for a few questions.
Professor Raghavan, I just want to say that I have used your Guru Shloka to start the morning. Thank you.
Hello? Hello?
Hello.
Couldn't hear you properly, Manjunath.
Yeah, I'm also not able to hear the other side.
Okay, can you hear me now?
Yes.
Guru Shloka in the morning.
Yeah, it is. Now,
When we started
4
the
a.m.
first session, we have used it. So for that, I must thank.
I don't hear you. I'm sorry, I'm not hearing you again.
Hey, computer. Yeah, they may not be able to. Here, yeah, bad network quality, it says. Okay, I'm sorry. Please
That's
continue. Hey, you tell
So
him.
let us thank Professor Raghavan again. Thank you, Professor
Sir,
Raghavan.
Professor Prasad is not able to connect from his internet connection. It seems like there is some internet glitches. He would actually like to thank that he has used your Guru Shloka in the morning inaugural function.
Oh,
That's
thank
what
you.
actually he would like to actually express.
Thank you. Thank you.
Thank you, Professor,
Okay,
for chairing the
thanks
session.
everybody. Thanks for